This question is on electromagnetism and focusing on your Fleming left-hand rule. A lot of students find difficulty in this question, so maybe to help you, let's look at another question, okay, which is in your 10 series, all right, 2007. Okay, we'll make use of this diagram before we go back to the question. Now, this question is what we are familiar with. You have, let's assume there's no current flowing through this copper wire yet, and this copper wire is rested, or you can say is pasted on the wooden block, and the wooden block obviously is resting on the electronic balance. So since there's no force, and then there's this magnet here, and you have to understand that the magnet is not touching, not in contact with any part of the electronic balance or the wire. Alright, so it's basically suspended there, you hold it there. So right now, assuming there's no current and the reading is 356. Alright, of course the actual O-level question is not asking about this, but let's refer to this. So let's assume right now there's a current passing through in this direction. And if you apply your Fleming left-hand rule, alright, I hope you can see the orientation. So the magnetic field is from north to south, so that will be this finger, and the current is going to the left this side, so that will be your conventional current, and the force that's acting on the wire will be downwards. That means to say there's a invisible force pushing the wire down, pushing the wooden block down, therefore the reading on the balance will increase. This is something that most of the student can do it, alright? But now let's go back to the other question here, which is slightly different. If you look at it, the difference now is the magnet is the one that is resting on the balance, and let's say you treat it as the mass of the magnet is 0.35 gram, okay? That is the mass of the magnet. And the wire over here is not touching the magnet. So if you apply the Fleming left-hand rule here, so the magnetic field is north to south, there will be this finger, and the current, alright, since it's a dot here, is coming out of the paper. Alright, so that will be, the second finger will be pointing directly out of the paper, perpendicular to paper. So you know that the force on the wire here will be upwards. So naturally, a lot of students will think that the reading will be similar to the question that I shown you just now, but actually it is not. Now, the Fleming left-hand rule is just we are applying on the wire, and the force is acting on the wire. But you must understand that the combined magnetic field of the magnetic field between the magnets and also the magnetic field around the current carrying wire, there's interaction between the two magnetic field, creating an unbalanced magnetic field. That's why it pushes the wire upwards. But many has forgotten is an action-reaction pair. So that means you push the wire upwards, there will be a force that's pushing the magnet downwards. One analogy is like, can you imagine you are pushing, your hand is, the arms are pushing the wire upwards, and your feet, you extend your body to push it up, and you're pushing the floor down, the magnet down. So that means to say the reading of this will have to increase. Alright, so now let's look at the option. So when there's no current, the reading is 0.35, that's the mass of the magnet, and when there's a current flowing through, what happens? It will be larger than 0.35. That should be the answer. Alright, I hope you understand now.